Alrighty, thank you for joining me. My name is Ethan Rido. I'm a technical marketing manager here at Desktop Metal, and today we're going to be talking about additive manufacturing alongside machining, or additive manufacturing versus machining. A little bit about machining, like most of you probably know, it's a very common manufacturing method, a subtractive manufacturing method. It's used to create a very wide variety of different part geometries across a very wide variety of different part sizes. As you can probably see on the screen, everything from very small parts to very large parts, from one part to even hundreds of thousands or even millions of parts, depending on the geometry. Of course, traditional machining carries some challenges with it. Like all traditional manufacturing methods, with really all manufacturing methods, there are some challenges to it. Specifically, these challenges really revolve around the first 1 to 100 parts. These parts are exponentially harder to produce than the next 100 to 100,000s. With these first 100 parts or 10 to 100 parts, this is really when the tooling is being figured out. You're developing fixturing, you're developing hard tooling, which makes these low volume applications very, very expensive. Because for each of these low volume parts, there's far more time per part that needs to go into them. There's lots of scrap and there's lots of setup time involved. So this is one of the main challenges we see when we're talking about machining, is the need to develop this fixturing. And we're going to talk a lot about this today. Some of the other challenges we see in machining specifically are these very, very long lead times. Generally, you can see 4 to 12 weeks. Here, we're talking about volume machining. We're talking about hundreds of thousands of parts, because this is when you're generating this hard tooling, this fixturing, to ensure you can produce parts quickly and at low cost. Of course, with that tooling design, you're going to see some large non-reoccurring NRE costs, both with the design of that tooling and fixturing, as well as the actual fabrication. Generally, unless it's a very simple shape, machining requires these relatively high-skilled, dedicated operators. You have your dedicated machinists who have lots of experience that can help you produce these complicated shapes. It can be a relatively industrial process. You don't see a lot of industrial CNC equipment in the office environment. You usually have that in a machine shop or a tool shop. And of course, all of you know that have designed for machining, you do have some geometry limitations, specifically around what your tools can reach and what your tools are able to produce, as well as what some of the fixturing needs are. The result of these challenges is generally we're seeing months to bring up a production line. Much of that has to do with this need for tooling. Less design iteration. You're once you have developed hard tooling and fixturing for your volume machining, you're really stuck with that design. You don't want to make any changes because you have to start this whole process over again. This is one that we're really going to be talking about today, is this need to sacrifice design optimization for ease of manufacturing. I commonly mention this as, kind of bending to the will of your manufacturing method, where you're much more concerned about, is my part going to be able to be machined quickly and affordably, than I am worried about, is this the best design for my application? And specifically, when we go to volume machining, you generally need to produce in higher volumes to help you amortize that volume machining fixtures. And while today we're talking about machining, these challenges and results are really true for all traditional manufacturing methods. Whether we're talking about casting or powder metallurgy, these challenges and results really resonate. Today, we're going to be talking, not just about the challenges and complaining about the challenges, but also talking about the solutions and some of the solutions that metal 3D printing can offer. We'll be talking about metal 3D printing as a complement to machining, how you can use it alongside your traditional machining operations, then also as a replacement, and a few scenarios of where we can actually replace our machining operations with metal 3D printing. And we'll look at both of these today. So, as I mentioned, when we're talking about metal 3D printing as a complement to machining, we're really talking about low volume. Talking about prototyping, jigs, fixtures, tooling, pilot runs, replacement parts, any application where the volume is quite low and I can simply print and maybe as a prototype before we move to volume machining and invest in that tooling. When we're talking about metal 3D printing as a replacement to machining, we're really talking about high volume. We're talking about mass production without the need for any tooling, any fixturing via binder jetting. We'll look at a bunch of examples of this today with parts that could have been machined, but were cheaper and faster to produce via binder jetting. The two printers that we're going to be talking about today are the Studio System. You can see it behind me here to my right. This is really the world's first office-friendly metal 3D printer. It's great for those lower volume applications that I was mentioning. It's very, very safe for the office. No hazardous powders, no dangerous lasers, no special facilities required. I'm sitting on my desk right here in the office, and the printer runs all day long behind me here. It has these very easy to use support structures. It has an automated workflow walking you through the entire design process and fabrication process, making it very, very simple to use. And it has these easy to change materials. Currently available for the studio system are 17.4 pH stainless steel, 316L stainless steel, H13 tool steel, copper, and 4140 low alloy steel. When we want to talk about some of the higher volume applications, we're going to be talking about the shop system, which you can see, the edge of here to my left. This is a binder jetting machine that's designed for machine shops. It's great for batch production of end-use parts, high throughput. You can produce hundreds of geometries per day, hundreds of unique parts per day, or hundreds of the same parts per day. It's very, very accessible still, turnkey solution. You don't require any third-party equipment, plug and play. It has very, very high print quality with over 670 million droplets per second, since it is a binder jetting machine. And it produces these fully dense isotropic parts that are great for end-use applications. So let's jump into it, and let's start with talking about metal 3D printing as a complement to machining. The first thing we're going to be talking about is your prototyping, your pilot runs, and your low volume production. With metal 3D printing, you can print these functional metal parts quickly and affordably during this development stage of design. You can print, batches to validate the design across multiple units before making this investment and placing these high volume orders. And unlike plastic 3D printing, which is very common for prototyping, we're no longer just printing to validate form and fit, but we can actually test our part to see how it performs under high loading, high heat, corrosion environments. Not just does it fit into my machine, but how does it actually perform in my machine? We're calling this functional prototyping, and we can now actually functionally test these parts. Of course, there's also great value in low volume, because when we're doing low volume or runoffs or one-off parts, we don't need to bother our machinists or sacrifice our designs. We can simply just print the part, install it in the machine, and we're ready to go. Great example of that is this e-bike bracket that I have with me here. You can see, this is used for holding a motor and a couple bearings, and then attaches to a bike for, to convert a bike into an electric bike. Rather than machine this part, all I had to do was optimize my CAD file, throw it on the printer, and in a couple days, I have the metal part ready to install onto the bike. What's cool about this part, especially in comparison to machining, is you can see all the cutouts that I was able to incorporate into this part. If I were to machine this part, I probably would have left all this solid, because, increasing the number of cuts is going to increase my costs. But since I'm printing, I can remove all that mass. It actually reduces the print time, reduces the cost of the part, and leads to a lighter, highly optimized component that actually makes this a better e-bike. Another great example is this servo-driven timing belt pulley. This is for a manufacturing environment. The original design that you're seeing on the left there was based on some aluminum extrusion. It then had these two, collar clamps. They were screwed onto either side with end plates. It required some extensive machining and was really not an optimized design. And the company here wanted to optimize it. So the goal was to create a part that was less expensive to manufacture. They wanted to lighten the weight, and then they also wanted to lower the inertia of this part to actually allow the servos to run faster. You can see that optimized design on the right. You can see the part that I actually have in my hand here, and you can see, a few more illustrations of it on screen here. Of course, this is a new design that's really taking advantage of 3D printing, and you can see those internal ribs and lightweighting features that would just be impossible to machine, that are really optimizing this part, where we're now able to go from a multi-part assembly down to just one geometry that can be produced faster, more affordably, and actually leading to a higher optimized, lower weight geometry. Another great example of using metal 3D printing as a complement to your machining operations is tooling. Tooling is generally some of the most expensive and most time-consuming parts to create. Generally it's produced in very low volume. It can be highly complex, and sometimes you need to use these difficult to machine tooling steels that are very, very difficult and expensive to work with. So one great application for metal 3D printing, especially on the studio system, is to simply print your tooling. If you need to, you can touch up dimensions on a 2.5 axis miller lathe rather than having to machine this entire block of steel and waste all that material and have that very, very expensive manufacturing operation. You can also do these new innovative tooling designs that now we're not limited to the geometry limitations that are so common with machining, and we can simply print our part and really optimize it for its application rather than for its manufacturing method, and we don't have to worry about all these limitations of machining. A great example of this is this custom end effector from our customer Egger Tool and Die. You can see the original geometry on the left, very, very simple. was costing them $216 per set to produce these parts, and they were weighing 1.2 kilograms per part because the parts were designed to be as simple as possible and be, where we're really optimizing it to be low cost to machine rather than, optimized for its application. On the right, you can see, we have this new optimized design. We were able to actually drop the cost almost in half to just $113 per set, 0.8 kilograms. So we reduced weight, which actually removes mass from the end of arm, which actually increases the performance and reduces the wear. And of course, is really just optimized for the application. You can see a couple pictures of it here actually in the actual assembly. And of course, as I mentioned before, that reduced weight with this optimized design actually extends the life of the servo motors in this automation assembly, really making it integral to increasing that production time and reducing the cycle time for this end of arm application. So now we'll switch over to talking about metal 3D printing as a replacement to machining. As I mentioned earlier on, the main challenge with machining is this ramp up. These very, very long manufacturer lead times and high non-recurring engineering costs that are required to set up volume machining. So while this is potentially very cost effective for mass production, these initial production is very, very challenging. Generally, as I mentioned before, you're seeing lead times of 4 to 8 weeks. You're seeing these large non-recurring engineering costs, and the result is really just a reduction in design iteration and a reduction in design optimization because you're really designing for ease of manufacturing more so than you are for the ideal application. So just to look at this in a little bit more detail and how we'll compare this to binder jetting, what does this setup time for volume machining actually look like? So when we talk to our machining customers, our large machine shops, our service bureaus, they generally say that when they receive a PO to start shipping out parts, they're looking at about 1 to 2 months of process. What does that entail? It takes about 4 days to determine the tooling, work holding, and cutters. You have to do some CAM programming to ensure it's optimized and actually is going to cut the right geometry. Then there's quite a bit of iteration. Generally, they do a pilot run with 100% inspection. They're going to do some iteration on the tooling as well as that CAM programming to ensure it's the right, getting the right geometries out. They're actually going to send these parts to the customer to get the customer approval, and then you're actually going to be able to begin volume production, usually after 3 to 6 weeks to start that production time. Of course, now what happens if this design changes? Now we have to make drastic changes potentially to our work holding, to our tooling, to our CAM programming that can set this back weeks, if not months, to the design process. Potentially we have to start this design process completely over for the tooling process, which can add lots of cost and lots of lead time to our production. How does this compare to our binder jetting process? With binder jetting, we're not talking months, we're not talking multiple weeks, we're generally talking 1 to 2 weeks. What does our process look like to go to volume production? You generally have your prep. It's about a 1-day process where you're going to maybe need to do a little bit of support design for printing and sintering, do a little build preparation to actually prepare that build. You're then going to do a pilot run where you're going to actually print, do the whole depowdering and sintering to ensure the parts are coming out adequately. And then you're going to, of course, get that customer approval. Maybe you need to tweak a little bit of support structures, a little bit of the design, but then immediately you can set that printer going and you don't have to make any changes to tooling, any changes to fixturing, because all we have to do is make changes to our CAD model, upload it to the printer, and we're ready to start printing. Of course, now what happens if the design changes? All I have to do is make a modification to my CAD file, load it up on the printer, and we can start printing hundreds or thousands of those parts a week without any changes to any hard tooling. So binder jetting really allows for mass production without tooling across a wide variety of geometries and a wide variety of quantities. Binder jetting has really emerged as this key technology for mass production. It uses this high throughput production area raster-based printing, as you're seeing on the right here, where we're able to spread binder over an entire layer of metal powder in just a few seconds. Of course, compared to a point-based process, this is very, very, very fast, allowing us to print tens to hundreds of times faster than other printing processes. We're also utilizing these low-cost, established metal injection molding supply chains that allow for a printing of a wide range of different materials. You get these isotropic material properties thanks to the sintering process, and you have these scalable large build boxes that allow for hundreds of parts or large parts to be produced. You can see the various different production scenarios that are possible. You could do something like on the left where you're doing a mixed volume, where maybe I want to print 10 or 20 different geometries all mixed together, all at the same time. If I have a lot of one-offs that I need to produce, you can do batch production where maybe I need to produce 10 of 3 different geometries or 100 of 3 different geometries, put them all together in a build box and print them all at once. And you can even do this mid to high volume production where we're producing hundreds or thousands of the same part per day, mixing all those parts into one build. Couple examples of this, looking at this power steering joint. This is a component that goes into a car power steering assembly, and it connects the electric motor to the actual steering wheel. This part's produced in 17.4 pH stainless steel for just $2.52 on the desktop metal production system. So hopefully, as you can see, with this process, we're really driving the cost down with binder jetting. Per build on the production system, we can produce over 650 of these parts and produce over 1.2 million of these parts per year. So we're really driving that cost down and increasing that throughput up. Another great example is this lock plug here. This is used for some industrial door locks. Traditionally has been made on a Swiss lathe, but with binder jetting, we can produce this part for just $4.71. We produce over 1,000 of them per build on the shop system, over 9,000 per week, really lowering the cost and increasing the throughput. Another great example here is this fuel swirler. This is used for pushing a fuel mix into a burner component. Again, produced in 17.4 pH stainless steel, costs just $4.95. Can do over 600 of them per build on the desktop metal shop system. Of course, now here, what if I want to make a change to the geometry? What if I want to alter the number of veins? If I want to alter the diameter, all I have to do is make a change to the CAD file, load it back up on the printer, and in a couple of days, I'm ready to produce hundreds of these parts. Another thing that we're going to talk about is that 3D printing really opens up these new design freedoms. No longer are we really just so constrained to designing for our traditional manufacturing methods that are very restrictive, but now we can open up these new design features that are no longer just possible in low volume, but now with binder jetting, we can actually produce in high volume. On the left here, you can see, very, very basic design of a pedal, originally weighing about 1,300 grams. It's really being optimized for, very, very easy manufacturing via traditional methods. Then you have your advanced additive manufacturing design. You're able to drop that weight by over half. You can see it's got some webbing, some features that would be very difficult to produce via traditional manufacturing, but are very, very easy for us to print. And now it's not just that we're going to print one of them for some special race car we're building, but now we can produce hundreds of those parts per day to actually go to market with an optimized design like this. You can see another example here. This is an optimized lightweight sensor holder, and you can see I'm able to incorporate all of this, lattice structures into the part to really reduce the weight. Where with 3D printing, it's actually possible to increase the complexity by doing something like this and actually lower the part costs. So much of part cost is associated with material usage. So by reducing the amount of material that's being used, we're actually reducing the cost. And again, it's not just that I can now produce one of these for some, special rocket ship or something like that. I can produce hundreds of these parts per day to actually go into, applications that are being seen every day that, we're interacting with every day on a much lower criteria. So lastly, we're just going to briefly, cover how these parts actually perform. We're using these metal injection molded parts that enable your parts to have quite excellent material properties. You can see on this chart here, if a raw material like you'd buy for machining is on that top there, our metal injection molded parts are going to fall really just below that curve. You can see the L falls right below it. So really just below what you get from a raw material, but still quite excellent isotropic material properties that allow for a wide variety of end-use applications. One important thing to know about sintered parts is that they are dense and they are polymer-free metal. Because of the sintering process, the history of the part and the fact that it was ever powdered metal has been completely erased. The grains have actually grown larger than the original powder particles, and the result is this homogeneous microstructure. This homogeneous microstructure makes these sintered powder metal parts very, very attractive in industrial applications because you're getting these isotropic material properties. Looking at just one of our materials here, 17.4 pH on our shop system, you can see that yield strength of 660 MPa. As sintered, can get up to 980 if you want to do an H900 heat treatment, and those material properties are exceeding those of MPIF standards. If you go to our website, you can download these data sheets for all of our materials. And you can really compare apples to apples to see how our materials are comparing to the materials you're using today. Another thing to talk about is density. On the studio system, our densities vary. If you're talking about our carbon steels, we're usually about 93.5% and higher. But with our 17.4 pH stainless steel, we're looking at 98% and up. On the shop system, currently we're printing in 17.4 pH stainless steel, and we're achieving densities of 98% or higher. As I mentioned before, all of these material data sheets are available on our website if you want to go out and check those out. Lastly, we're going to look at how do these parts machine. I know a few times today I've mentioned, you may need to touch up critical dimensions on the machine. And one thing to note is that these materials machine extremely similar to your wrought material. You can see a couple different operations that were done to this part here, a facing and a thread milling. And you can see the different tools and mill settings that were used, but it's very, very similar to your wrought material. And our 17.4 pH printed is going to machine very similar to the wrought 17.4 pH that you're buying from your material supplier. That's all I have for you today. Thanks so much for joining me. I hope you learned something. I hope this was useful for you. Feel free to shoot me an email if you have any questions, thoughts, comments. I'm also always happy to hop on a call to discuss any of your applications, to talk with you about your metal 3D printing, to see where we can potentially add some value, to see where you can make some use of metal 3D printing. Happy to look at your parts or geometries to let you know what they would cost, what the throughput would be on our systems, to help you understand, is this a good technology for you to make use of? Thanks again, and I hope everyone has a great day.